Hello there, children. Are you ready for another wonderful presentation by your awesome teacher, Miss Byron? Oh, good. I'm so glad you said yes. All right. So this is going to take you through electron configuration basics. So what we're going to talk about is how to construct an electron configuration for almost anything on the periodic table. And by almost anything, I mean anything. So the first thing that we talked about, or the last thing we left off at, was Schrödinger and how he had a box, and inside of that box was a kitty friend. Doot, doot, doot. There's kitty friend, can't you tell? Doot, doot, doot. And he also had in that box, if you remember, some sort of nuclear waste, and he also had some poison, because, you know, what else do cats like in their boxes? So, as long as the box is closed, we don't know if kitty friend is either dead, right? Doot, doot, doot. Dead kitty, or live kitty. And so the point he was making is that the cat exists in both states at once. And that's very similar to our electron, because we've been talking in school about how it has that dual nature, right? So the other reason why Schrödinger is really important is because he was the first dude who came up with orbital theory. And so if you remember from class, orbitals are regions of space where electrons are most likely to be. And so what I've done here is I have labeled two things. I have school right there, which I work at, and home right there, which you will never visit me at. So now what we've got is we have a path, right, where I start at home and then I commute on Route 2A, whatever, over to school, and I do spend a fair amount of time there, and then of course I commute back home. And what you end up seeing, and we talked about this in class, is if you map out my positions, you'll see that I spend a large amount of time here, and I spend a large amount of time here, and in between, not so much. But I am there every once in a while, right? So there's these two areas of probability where I'm most likely to be at any given point in time. Now, does that mean that I don't go off over here to France? No. I'd like to, but I definitely could be, right? So this all gets back at that whole probability theory thing. So what we're going to do now is we're going to define what these orbitals, or these regions of space, look like inside of an atom. So here we've got the names of a bunch of different orbitals. So these are all the different types of orbitals that there are inside of an atom. So the first one we've got is called the s orbital. That one's going to be the one that is lowest in potential energy, and it's the closest to the nucleus. Then we have the p orbital, which is a little bit further away, but it is in the same energy level. We've also got d and f orbitals here, which I'm really going to attempt to draw only briefly, because really they get into like some serious sort of weirdness, and I don't really care. So let's see. As far as drawing these things go, the s orbital is pretty straightforward, right? It is a sphere. And so remember, these pictures aren't actual things. They are just a region of space that tells us where an electron is most likely to be. And so you can look, right? It's a circle that encompasses the closest spot to the nucleus. That's why the S is the lowest energy of each of the orbitals. So this one is a sphere. Now, if I also draw the p orbital, this is where things get a little bit tricky. So what I'm going to do is, I think, I'm going to try to divide this up because the p orbital is broken up into px, py, and pz areas. And what they look like is, if you imagine a graph, kind of like in your math class, right? We have a y-coordinate and we have an x-coordinate, and then if you guys have done any three-dimensional work, you also know you have a z-axis that kind of cuts through like that. So that is the way that these ones are organized as well. So a px is going to go along the x-axis, and it's kind of like that. And if you think about it, it makes sense because that means these areas that are out towards here, right, and out towards here are a little bit bigger because electrons repel each other and they don't want to be near each other. Hence the reason why that area that's smack in the middle has virtually nothing. It's because they do not want to be near each other for any circumstances. So that is along our x-axis. Our py looks very similar, except that one is along the y-axis. There you go. And electrons are more likely to be found on the edges. And then pz, I just kind of draw the same thing but on a diagonal. See? Can't you tell it's three-dimensional? So that's what they all look like. And so if I put all of the p orbitals together, so I would get something that looks like this. So here's px, here's py, and then here's pz. And you can see how it kind of starts filling up an awful lot of space, right? And so eventually you'll get to that normal model of the atom where everything smooshes together, and that's what you see is just a sphere. So d orbital gets a little out of control. D orbital is based on, and you don't need to know this, it's like a clover, like that, except there's one in the x, and there's one in the y, and there's one in the z, and there's like a donut for some reason that like goes around the middle. So anyways, and then F is just like, there's a picture in your book. I'm really not interested. It gets into weird like fourth dimensional stuff. So let's see. Yeah, let's get rid of that. No one wants to see you anyways. So what you get when you start putting them together is you'll get a sphere and then a little bit higher energy, so that means a little further away from the nucleus you'll have a P. So I'll do all my lobes, right? And then you can have another S because they can overlap. Then you can have another P. Missing one. Yep. And then another S. And then another P. And then maybe a D. So now we've got some cloverage going on. And of course the donut. And hey, guess what that starts to look like? A circle. So that's why the current model of the atom just kind of looks like that. And on the inside, remember, it's got that little thing, and it says 90% of the time, I'm going to find electrons in there. That is our quantum mechanical model. So now that we've identified our regions of space, so our S looks like that, our P looks like that, and then our D looks like confusing, and F looks like even more confusing. Let's try to put this to use. So the cool thing is about the periodic table that it's divided into areas where each atom that lives there, their electrons like to be. And so if you look, we have something called S block right here, and helium actually does fit into S block. It fits right there. We have P block, which is the next highest energy. That one's right here. Then we have D block, which is right here, and then we have F block, which is way down here. And each one of these orbitals is capable of holding 2 electrons. And so if the S orbital looks like that, that means I can hold 2 electrons in there somewhere. And if you remember from bio, they do that 2, 8, 18 nonsense. We're not going to do that, but it does tell you how many are in each energy level. P block, there's a rule that says only 2 orbitals, right, one orbital can hold 2 electrons. So there's my px orbital, which means 1 electron will be here, 1 electron will be here. They run away from each other because they're negative. Same thing in my py, doot, doot, doot. 1 will go there, 1 will go there. And then my pz is diagonal, 1 there, 1 there. And so what that means is my p block can actually hold, what is it, 2 electrons here, 2 electrons here, 2 electrons here. If we add those all together, 2, 4, 6, it'll have 6 electrons. And that's really convenient because if you look at p block on your periodic table, there's 1, 2, 3, 4, 5, 6 blocks it moves over. Handy dandy, right? If I check out S block, S can only hold 2 electrons, 1, 2. It's like it was meant to be. D block can hold 10 electrons, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, which means D block actually has 5 orbitals in it, right? 10 divided by 2. And then F block, because it has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. That means that F block actually has 7 orbitals in it. So the periodic table is pretty well organized for you to figure out where its electrons are living, like where the electrons are in each atom. So the other thing that we are going to need to do is we are going to need to identify energy levels here. And energy levels tell us how close we are to the nucleus. So if I use a different color, let's pretend we've got our protons in here, right? Here's my nucleus, right in there. Our energy levels, according to the Bohr model, kind of look like this. They get a little closer together as they go out, right? So the closest one here, closest one to the nucleus has the lowest potential energy associated with it. So things are going to be the most stable there, and that's because those electrons are attracted to the nucleus, and so they're pretty happy there. The furthest away is going to have the highest potential energy. So what we need to define then on our periodic tables, we need to define where these energy levels are on our actual periodic table, this friend. So what I'm going to do is get rid of the annotations over here, and we're going to write in according to each row. Just number them down. 1, 2, 3, 4, 5, 6, 7. So there are 7 energy levels on this periodic table, and the way they're read is they're read across this way. So hydrogen and helium are in energy level 1. Those friends are in energy level 2. Those friends are in energy level 3, and it kind of like goes on and on and on and on. Yes, of course, it'll get more complicated, but we're going to take it nice and easy so far. So let's try practicing. So what I've got is I've got an arrow and I've got my periodic table, right? Here's my periodic table. Here's all the energy levels that I put in for you. And what we're going to do is we're going to take it element by element, and we are going to assign the electron configurations of the stuff that's just in S and P block only for now. D block and F block get a little more complicated, so we're not going to do that till later. So we're going to take it step by step. That little friend is going to stay up there, and I'm going to start out by doing hydrogen. So hydrogen is the first element, right? And Our electron configuration is composed of three things. So the electron configuration for hydrogen is 1, S, lowercase s, and then number 1. And they each mean different things. So that first one right there corresponds to the energy level. So what row is it in? That's how you can figure that out. What row is it in? So hydrogen is in the first row. That means it's in the first energy level. The next one is what block is it in? If you remember, this is S block, this is P block, this is D block, this is F block. And hydrogen right now is living in S block, so that's where we're going to start filling its electrons. This last number is how many electrons are there in that orbital. And in this case, hydrogen only has 1 electron, right? The other way you can look at this is how far over do I have to count to get to the element we're talking about? So I'd have to count over 1 to get to hydrogen. I'd have to count 2 to get to here. 1, 2, 1, 2, 3, you know, on and on and on. So that is the electron configuration for hydrogen. Now, oh no, where's my arrow? What we're going to do is we are going to do helium next. Okay, so let's put him back. And let's look at helium. So helium, first number corresponds to the energy level. What row is he in? Oh look, he's in row number 1. So start with a 1. Now, what block is helium in? And if you remember, helium actually fits into that empty spot right there in the S block. So we're going to call him in the S block, so 1s. And then if he were in S block, how many over would I have to count to get to him? I'd have to go 1, 2. So his number is 1s2. Hopefully that's not too bad. Now, let's see what else we got. Let's do lithium. Li. So now things are going to get complicated. What we're going to do is we are going to read this periodic table like a textbook, right? And when you're reading text from a book, you always start at the top line and you always read left to right. And only after you're done that sentence are you allowed to go down to the next one and read across there. Then you go to the next sentence and you read across there. Then you go to the next sentence and you read across there. And that's exactly how you have to do electron configurations. So even though we're starting at lithium right here in the second energy level, the first one is already filled and we can't forget that. So lithium itself has 3 electrons. So that means we need to place them somewhere. So what I'm going to do is I'm going to start with my first electron. So my first energy level needs to fill first. So I'm going to start at the top of my book, top of my page, right? And I'm going to read across. So right now I am in the first energy level. So I'm going to put a 1. I am also in S block, right here. So I'm going to put an S. And in order to completely read this line so that I'm able to go on to the next without any missing information, I need to go over 2. So I have to count hydrogen and helium. So 1s2 is where I'm at right now. And now that I'm able to do that, I can go on to second energy level. If you look, lithium right there is the first one in the second energy level. So now I am in second energy level. What block am I in? Well, it looks like I'm still in S block right over here, and it looks like I have to count over 1 to get there. So S block, count over 1. And if you look, this is the trick to making sure you know you're right. If you add up the numbers that are the exponents, they tell you how many electrons you've used. I've used 3 electrons. And guess what? Lithium has 3 electrons, so I'm good to go. So that's how lithium works. We're going to keep going. So why don't we do, oh man, I'll just do that. Beryllium, B-E. So beryllium, I need to start here. I need to read across my first line, so I need a 1s2. Now my first line is finished. Now I'm going to go on to my second line. 2, I'm still in S block, and I need to count over 1, 2 to get to beryllium, so 2s2. And again, if I add up my electrons here, 2 plus 2 is 4, beryllium has 4, I'm good to go. Let's see, I want this friend. So now let's go to boron. Boron is in P block, right? So, same rules apply. Start at the beginning, read your line, then read your line. So, this one is boron. I need to go 1. I'm in S block. I need to go 2 over. So that's 1s2. Then now I can go on to my second line. 2. I'm in S block and I need to go over 1, 2. So now I can add a 2s2 to my configuration. I'm not there yet. So I've accounted for 1s, I got all the way here. 2s, I went all the way there. Now I need to enter P block. So I've already counted these 2 spots right here. I am still in the second row, right here, right? I'm going over 1 in P block. So because I'm still in the second row, I'm going to write 2. Now I'm not in S block anymore. I'm in P block, and I need to go over 1. Ta-da! So let's see. Let's just double check, right? 2 plus 2 plus 1 is 5. Boron is 5. We rock! So let's do some harder stuff. Let's do, I don't know, we'll do oxygen and then we'll skip to neon. How's that? So, let's do oxygen, oxygen. So, are you getting the point yet? 1, S, 2, 2, S, 2, still in row 2, 2, this is P block, P, and then I have to go over 1, 2, 3, 4. So, 1s2, 2s2, 2p4. And again, all of my electrons should add up. 4, 5, 6, 7, 8. Bingo! Rock star. Alright, so that's S and P block. So, what I'm going to do is, I'm going to take, if I can find where the eraser went. So, maybe I can just get rid of this stuff. Yeah, let's do that. Let's get rid of all this nonsense. Alright. Doesn't that look fun? That looks like a fun electron configuration. Yes? Alright. Here. I want you to do the electron configuration for, let's do silicon. Let's do that one. And so, pause the video here if you don't want to see the answer, and then you can come back and you can start the video again, and I will do it for you. Alright, here's silicon. So, we've got 1s2, and I'm done my line. So, 1s2, then I've got 2 S block, and I need to count 2 over. So I've got 2s2. Then I've got done in S block, going over to P block. I need to go all the way through P block, and remember that has 6 stops. So I have 2p6. Might need another line for this one. Then I've got my third line, 3s2, 3s2. I think I'm good, maybe. And then 3, still in the third row, p1, 2. Full of win. Yay! Alright, so if you want to keep going, I'm going to do some more complicated stuff. I'm going to do D block and I'm going to do F block. If you're ready. So, same slide, different block. If you remember from before, D block is all this stuff in the middle. Okay, 1, 2, 3, 4, 5, 6, 7, 8, 9. There are 10 columns to D block. That means it can hold 10 electrons, or another way to say it is, it has 5 orbitals. So, the thing with D block is, if you remember our picture of the atom, right? Here's our nucleus, and we're getting further and further away, right? So S block is pretty close. P block is like, you know, it's like our clovers, right? Or our lobes. And then now we've got D block, which is our clovers, and we're getting kind of far away. And so what that means is it's really high energy. And in fact, the energy is so high that things that are in D block are kind of artificially raised up in energy level when they're not supposed to be. For what I mean by that is, see this row right here? If we did this electron configuration just like we did the last few, we would have said 4s2, and then to get into here we would say 4d, and then like whatever, however many we have to count across. That's actually not the case here. So this row right here that's in row 4 is actually 3d. So what happens is this section needs to be kind of like pulled up a row artificially. Or the way that you can remember it is, if you're in D block, you need to subtract 1 from whatever energy level you're in. So N stands for energy level. So I'm going to show you how that works. So let's try scandium. And that is the first one in D block. So if we're going to do SC, I'll write in red. Remember, we need to start from the beginning. We need to start up here. We need to go across our rows all the way until we get to scandium. So I'm going to assume that you already know how to do that. So SC is 1s2. Now I'm in the second row. I have 2s2. Then I have 2p6. Now I'm in the third row. 3s2. Now keep going in the third. 3p6. Now I just finished 3p6. I just finished here. Now I'm at 4s2. And now I have officially encountered D block. So, if you remember, D block is kind of artificially high. It's really not the 4th energy level. It's really the 3rd. It's just so high that, you know, roughly speaking, it has the same energy. It's like an intermediate energy between 4s and 4p, so that's why it's smooshed in there. So it's 3d1. So that's how that works. I'll pick another one in here to do. Actually, let's get rid of that. I'll pick another one in here to do. So let's get rid of that too. Let's do cobalt. How's that? Or let's do a bigger one. Ruthenium. How's that? 44. big. So I'll have to write kind of small. So RU. Are you ready? All right. 1s2, and then 2s2, 2p6, 3s2, 3p6, 4s2. So now I'm right here, and I'm just about to do the first transition into D block. And I have to go all the way through this section of D block so that I can get back to P. And D block is the only one that you have to subtract 1 from, because right when you get back into P, this really is the 4th energy level. So we have to go back to the 4s there. So I just did 4s2. So I just took care of those. Now I'm going to do 3d10. That's my next step. So 3d10. So I just did those. And now I'm going to go into P block. I have to finish out my line before I go on to the next one. So now this is going to be back to energy level 4, 4p6. From here, right, I just finished out my 4p6. Now I can go on to the 5th energy level. So that's a 5s2. I'm going to write this on the next line. 5s2. And now I'm done my 5s. I'm going to go into D block, which means I have to subtract 1. So this is going to go to 4s. And then I have 1, 2, 3, 4, 5, 6 over to go. So this is going to be 4d6. Ta-da! That is how you do anything that's in D block, or anytime you have to get through D block. So if you want to see how to do F block, we'll do that in the next slide. F block is the dangerous ones. These are all the radioactive ones. So let's do those now. All right. So here's our periodic table. And what we've got is we've got F block all right here. So the weird thing about F block is it's kind of a time warp. If you look at LA and AC, and then you look at these spots right here, see how that's a little star? Lengthenide series right there, actinide series right there. They kind of fit in the periodic table right there. But, you know, because it wasn't as pretty and whatever, Glenn Seaborg actually said, nah, we're going to take them out, we're going to put them in their own section. So this is F block. So as you can probably guess, right, with D block, what we did was we were getting so far away from the nucleus that that we had to subtract its energy level by 1. So in between this, here's our 4s, this turns into 3d, and then back to 4p. It's just that that third D, 3d, is so high energy that it's kind of stuck with the 4s. Well, the same thing happens with F block, except when you're in F block, you need to subtract 2 from the energy level. And so what this means is, see how 57 really fits in there, and that's the 6th energy level? This is not 6F. Because we have to subtract 2, this is really 4F. So the 4th energy level has an S, which is right here. The 4th energy level has a P, which we know is right here. It's all in the 4th row. The 4th energy level also has a D, which is artificially in the 5th because it's much higher energy. And the 4th energy level actually has an F as well, but it's way down here in F block, really far away from the nucleus. Okay? That's why those things are super unstable. That's why they're all radioactive. So what we're going to do is we are going to try to sort through F block. And F block is a little bit tricky based on where you land. So what we're going to do first is we're going to pretend that we land either here or here first. And depending on the periodic table that you see or use, this is actually a little different than the one we use. Depends on whether LA and AC are plugged in here, or if you look on this version, LU and LR are right here, and usually those are actually found on the very end. So what's going on is we've actually got not 14 across, we've got 15 across. So sometimes some guys fit in here, sometimes other guys fit in here. So there's some sort of flux. So because atoms would like to be the most stable they can be, their electrons are going to want to be closer to the nucleus if they can get away with it. And so what happens is, if we're doing the electron configuration of either La or AC, they do fit in right here. They're not F1s. They're actually D1s. So if I do the electron configuration just real quick for La, I might need a lot of space for this. I'm going to run through it, I think. Here, I'll say La just so you can't get confused. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, where am I? 3p6, 4s2, 3d10, 4p6, 5s2, and 4d10, and then 5p6. Am I there yet? Where am I? 5p6. 5p6. Aha, I'm almost about to get to F block. 5p6. Now I'm going to go to 6s2. I'm going to write that one in. 6s2. And so I just finished those. Now I'm at my time warp, right? So what I just told you is if I land here, if I'm trying to find the electron configuration for La, La acts as a D1. Because there's nobody in that D orbital yet, the 5D, so why can't it live there just for a little bit? It's more stable that way. So it's going to be 5D1. That's if it's La. Now, let's get a little more complicated, shall we? So, let's move La out of the way. That was awesome. Doot, 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 doot. And let's switch it up so we're doing CE. So instead of landing there, now we've got 2 electrons that are similar in energy. What are we to do? So, here we go. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 4d10, 5p6. Am I there yet? Where am I? 5p6. So again, just about to enter F block over here. 6s2. Now I'm about to enter F block. Because I have 2 electrons that are similar in energy now, because we're going to CE, they can't both occupy D. There's not enough space for what they need here, because there's 14 electrons in F block. These are such high energy now, especially since they're repelling each other. They want nothing to do with each other, right? So they need that extra space in F block. So what happens is we're going to go from 6s2, and then we're going to drop down to 4, because remember we get to subtract 2, 4f2, 4f2. And that's how you do anything that's past LA, is that they're all going to be in F block. They're all going to be in F block. So here. So LA and AC will be D1. Anything past will be in F block until we get, again, to LU and LR. Remember how I told you guys some periodic tables write, get out of here, LU and LR at the end over here. So the most important thing you want to realize is that you need 14 electrons here. So if we're using LA and AC as part of F block, they count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. There's my 14 right there. And so I can't have Lu and Lr join F block. There's just no room for them there. So they do get bumped to the D block spot. So we already did La, pretending as if La were plugged in right here. Now let's do Lu. And if you look, you need to go in numerical order. So 55, 56, 57, 58. So in order to do Lu, it's not the same thing as La. La was just 6s2 and then 5d1, because remember he's plugged into here. Lu is different because now we can't just go out of numerical order. We can't go element 55, element 56, and then element 71. We're missing so many electrons down here. So Lu is going to have an F block added to it. All right, so let's do Lu. So Lu. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 4d10, 5p6, 6s2. All right, so now we're getting, hello. All right, we're right here, 6s2. See that? Now, because we're not stopping here at D1, we need to go through this whole block right here. So I was in 6s. I'm going to drop down to 4f. And I need to go all the way across. So that's 4f14. So now I've just taken care of all of this. Now I time warp back up, and now we're where Lu is. And Lu is in the 6th row, but it is in D block, so we have to subtract the 1. So it's 5D1. So that's how F block works. It's pretty crazy pants, is it not? So, there you go. There's the craziness. I'll do one really hard one for you. How's that? Let's get rid of that. No one wants to see these things. And then, let's see. Let's do uranium. We were doing fission last chapter. Why not? Oh, this is going to take a while. So, uranium. Hey, you. Learn electron configurations. 1s2, 2s2, 2p6. See how small I'm writing? 3s2, 3p6, 4s2, where am I? 3d10, 4p6, 5s2, 4d10, 5p6, 6s2. So now I'm right here, and I need to go to my time warp down to F block and read all the way across there. So that would be 4f14. Now I am back up to D block. I'm in the 6th row, but remember D block is -1, so it's 5d10. And then, as I keep going across, I exit 5d10, and now, bam, back into 6p, 6p6. So now I am out of 6p. I get to read down the next line, 7s, almost there, 7s2. And then it looks like, so uranium is not stopping here at AC, so it's not going to be a D1, so I'm going to keep going into my Fs. And I need to count over 1, 2, 3, 4. And in F block, I have to subtract 2 from my energy level, so it's not 7, it's 5, F4, because I have to count over 4 to get to uranium. Do, 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 do. Winner, winner. And then we've got, that's about it, I think. Do, do, do. So, hopefully you enjoyed your past 12,000 hours. And now you can practice. And if you want to watch this again, if you want to practice, you can. So uranium is a really big one you can practice. And one of the other ones I did in here for practice too, I think it was scandium. So go back, try those, and tell me what you think. All right. Bye-bye.